Okay, welcome to this webinar. And my name is Yoshihiko Horio from Tohoku University. And the title of the talk is this Brainmorphic computing paradigm and hardware. And this is these are contents of my talk today. Introduction, Brainmorphic computing, what is that? And briefly touch to the requirement for Brainmorphic hardware. And then I will show you what is the difference between Brainmorphic and digital hardware systems. And introduction, we have two items. First one is von Neumann bottlenecks. Okay, we have two bottlenecks actually. The first one is a well-known bottleneck, which is hardware bottleneck for von Neumann stored data architecture. So this is the basic structure of Neumann-type computer. You have input devices, output devices, and controller, of course. But the important part is a central processing unit, CPU, and memory devices. All instructions and all data are stored in memory. And if a CPU wants to do something, the CPU have to read instruction and data from memory device. And then after there's some calculation, the CPU have to write back the data to the memory device. And if necessary, the change of instruction will be write back to the memory device. So each time the CPU do something, this loop happens. So if we want to speed up okay. There's one more video. Oh, sorry, maybe. Okay. So anyway, to speed up the video, the communication here, the processing here, we have to make this communication very fast. Okay. So this serial transmissions of instructions and data between CPU and memory should be accelerated for high-speed communication. Okay, so the transmission speed of this loop will determine the upper bound of the computational speed. And also, for the hardware point of view, this will be very high frequency. So this loop will consume a lot of power. So this induces a power limitation of the hardware. Therefore, this loop of transmission gives physical limitation of computational efficiency. Okay, this is called Neumann Bottleneck, and this is the hardware bottleneck. The second one is software bottleneck, which is programming and algorithm. And this Neumann Bottleneck was used by John Bucks for the first time in his lecture, in a Turing Award lecture, like here from Neumann Bottleneck, and said that not only these two are little bottleneck for the data traffic of the program, the two means a vacuum tube at that time. So nowadays this should be a transistor. So this shows the hardware bottleneck, but more importantly, it is an intellectual bottleneck that has kept us tied to a world at the time thinking instead of encouraging us to think in terms of the larger conceptual units of the task at hand. So this is the bottleneck between a Neumann-type computer and brain for the way of thinking. We usually take thinking as a conceptual way, but Neumann-type computers should take a word at each time. That restriction actually came from the hardware bottleneck. So this gives an intellectual limitation. So this is also called the Neumann bottleneck. Okay, so we have two Neumann bottlenecks. Those actually have restrictions and limitations for the current digital computers. The first one is, of course, inherent low power efficiency because of the hardware bottleneck. For example, Fugaku consumes 40 megawatt of power, which is greater than 90,000 households consumption, power consumption. So we may need some thermal power generation plants. And another example is here, the IBM people actually made a neural network simulation with this much of neurons and this much of synapses. These numbers are actually comparable to the human brain in 2012, using the Blue Gene computers over almost 100 lakhs, and with those humongous number of processors, memory, and threads. They actually obtained the speed of almost 500 times slower than the brain from this simulation. So from this result, they estimated the power consumption of the supercomputer, which can run with a comparable time scale of the brain. Then they get the number here, 12 gigawatt. This much of power is almost the same as the 10 units of the nuclear power plant. In contrast, brain consumes only 20 watts with very little volume. And at that time, they realized that, for Neumann-type computer is not good for brain-type computation. So now, so after that, they started to develop brain-type computers such as True North chip. And second restrictions are the transmission basically serial. So basically serial processing. So the true parallel distributed processing is impossible. And however, the brain uses parallel distributed representation and also processing. And again, the memory and processing are not separated, but integrated. This is unlike to the von Neumann type architecture. Third one is, of course, program, which is software bottleneck. These days, the programs are so huge, so that fat and weak, and explosion program usually happen. And however, there's no external or explicit program in the brain. And evolution, continuous learning, and adaptation are used to improve the performance of the brain. Okay, fourth one is that computation is done in discrete time using the quantized value of the variables. So it is kind of hard to make a high-dimensional real-time spatial temporal processing. However, brain uses continuous spatial temporal processing scheme with high-dimensional complex dynamics. Okay. Besides these restrictions and limitations came from the Neumann Bottleneck, the digital computers currently has facing some technological problems. One of which is the stall of the Moore's law. Moore's law has been long has been the driving force of development of the digital computers, but it's stalling. And also the manufacturing cost using the state-of-the-art semiconductor process is very expensive right now. It's surging actually, and this will be one of the technological program. However, the driving force for the improvement for the brain processing always exists throughout the life period by evolution, adaptation, and learning. And this is the front page of the IEEE spectrum in 2015 that says that the Moore's law is dying. Okay, and the more important, so the important one is the last line, and that could be good. Here means that we have been tied to the Moore's law, but now we are free from the Moore's law. That means we can endeavor or explore the new kind of computational paradigm. So they said that that could be good. Okay. So the second item of in the introduction is non-von Neumann computers. So currently we have much expectations for the non-Neumann type computers. The typical candidates are quantum computer and brain type or a neurocomputer. In this webinar, we just concentrated on this brain type computer, especially for the Brainmorphic computer today. Okay, so before going to that, to the Brainmorphic computing, we'd like to just review how the digital computers are developed so far. Actually, digital computers, development of digital computers started from principle, which is Boolean algebra, and then von Neumann proposed the architecture, which is von Neumann architecture, and to make this architecture efficiently, the technologies have been developed. In the early era, the vacuum tube was used, and then BJT bipolar junction transistors were used, and now almost all the digital computers are constructed using the CMOS digital devices circuit. So this is done by top-down approach, and those principal architecture and technology were much very good. Okay? Actually, there have some effort to make brain-like computers, and this one is early neurocomputer, which is around 1980 to 1990, and based on the neural network or machine learning principle. However, at that time, the hardware used the von Neumann type computers, so there's a big mismatch between these two principle and architecture. Currently, neural network-based AI accelerators, such as deep neural network, takes some tricks in architecture, for example, in near memory or in still learning, but this is not really non-Neumann. So there's still partial mismatch exists here. And also because of the change of this architecture, there is some partial mismatch between the technology and architecture. So the current artificial neural network on the AI accelerator approach will not reach the goal of the brain type computation. So what should we do? What we do is we should take the bottom-up approach, not top-down approach, because we don't know yet what is the brain computational principle. Yeah, not yet. However, we have much knowledge right now at hand for the constitutional elements of the brain, such as neurons and synapses and barriers. So if we can make such elements, or we can mimic the dynamics and functions of those kind of elements, and if we can connect to make a certain brain architecture, learn from brain, maybe we can get, well, we can emerge some aspect of the brain function, which will contribute to decipher the brain computation principle. So we are now taking the bottom-up approach to the brain-morphic computation. Okay, currently this is the very good chance, because we have new device technologies such as nano device technologies, organic device technologies, and also we have now gathering much knowledge from brain science, thanks for some technology development for the measurements, such as functional MRI or some genetic genetic techniques. Okay. And the important thing is the change in computational principle here, and the implementation of that principle will naturally lead to a brain-specific computational paradigm, which digital computers do not have. And more importantly, the resulting hardware should be efficient and have a high performance, because the principle itself was changed to do so. Okay, this is very important point. Okay, let's move on to the brain-morphic computing. So first item is brain, about the brain, and we have 4 items in this chapter. Okay, so brain, what for? Brain was originally developed for the life support system, so to support the life itself. So first we have the body and some brain, and then to support the body, the brain actually invented some specific or information processing like this, and then maybe the new sensor or new modality was added, and also there's some structure change in the brain occurred. Then the new information processing emerged again, and this kind of loop is repeated over time and time in the evolutionary process. And the important point is the structure, which is the body and the brain, and function, which is information processing, were co-evolved through the development. So we cannot divide structure and function here. So we have to take care of both of them together. Okay. So structure and function are co-evolved. Okay. The other aspect of brain is here. The brain is this one, and we have body, and there are world, external, which is called embodiment, which is usually unsteady, noisy, unknown, and certain predictable or limited in as an API. Okay, so we have here the boundary between our life organism to the external world, which we call the let's call this is body or organism boundary. In contrast, body itself has internal world, which is called the internal milieu. The internal milieu is usually kept steady. This is called homeostasis. But some researchers call this is homeodynamics, because the internal states actually fluctuate somehow, but very narrow limited range. In any way, there is another boundary from brain to the body world. We should call this brain boundary. And the brain actually have to interact to external world, which is environment, and also the the internal one, which is internal milieu. So brain have to interact both of them. And if you look at here, for the interaction, brain always should, the interaction should always go through the body. And here, and this is also through the body. So the effect of the body should be counted. This is called the embodiment. Usually, the internal milieu and the external environment are connected to the brain through some very high dimensional dynamics. The other important point is this brain has extremely high structural complexity because the brain evolved by building new parts on old parts. So this high complexity and embodiment emerged the brain specific information processing scheme like this. And one important aspect of this kind of brain processing is the processing through process as a whole system. The process is kind of difficult to explain, but if you look at the life process, you can maybe understand the life process. It says that a life process is a kind of property of a life or organism, and you cannot divide that life process, for example, by half. Then life will disappear. Okay, it is almost the same meaning here. This is a kind of property of the brain as a whole. So this is kind of not an algorithmic process. Okay, anyway, these brain specific computation paradigm is a target of the brainmorphic computing. Okay. Okay, so I emphasize that the structure and the function are tied together. So first, what is structure? Okay, so this is this figure shows the evolution of the brains of vertebrate, and this is common descent of vertebrate here, the lamprey, and we have shark, and salmon, frog, and lizard, and pigeon, and human. If you look at the figure, there seems to be very different than the variety of shapes. But if you look at closely, we have H species MDC or T, those are listed here, upon the above. If you look at this figure, all the brains have the same parts. Okay, so we can generalize the structure of the brain of vertebrate like this. Okay, so we have this is the basic design of the brain of vertebrate. So the special feature of this type of structure is we have several different parts, which is specialized circuits. And each specialized circuit have specialized function. And those circuit and function are actually co-evoluted. And if we don't have circuit, we don't have function. If we don't have function, we don't have circuit. So those are tight interdependency. So let's call this a consolidated craftsman. Craftsman means the craftsman with specialized circuit and specialized functions. So this kind of consolidated structure we have to think. So this gives a process of information. Okay, so we have to think about this kind of structure to realize the brain type information process. Okay, for the engineers, structure means hardware and function means processing. So hardware and processing should be tied together and cannot be divided. Okay, so what kind of structure? Actually, this is multi-scale, multi-layer, multi-feedback structure. If you look at the brain in some levels, but you can find that multi-scale, multi-layer, multi-feedback structure in every level of the brain. So this is one structural feature. And if you look at the circuit level or area level, you will find this kind of peculiar multi-nested layered structure. Okay. So this is the this figure, like rose flower, includes neural networks, which are actually recurrently connected. So we call this nested layer with recurrent structure. Those nested layers, several layers actually connected from the bottom with the convergent connections, and also connected from top for the divergent connections, bidirectional. And also, there are several lateral connections. So this gives a very complex structure complexity. So we call this unnested layer of nested layers. Actually, layer structure, but each elements are nested layers. So this is the very complex structure complexity. This gives a structure complexity, and compared to some random structure or regular structure, this is the very complex. And so this will give the basis of complex information processing. So if you think about the complex information processing in the brain, we have to think about this kind of complex structure. Okay. So what is function we expect? So this left-hand side is brain or brainmorphic computing, and the right-hand side is digital computing. Okay, because of the embodiment, the brain only have limited resources such as small data, memory, and energy. However, we have to solve the problem in real time, otherwise we will die. Okay. However, the world is ethereal and uncertain, dynamic, and continuous, very high-dimensional world, and the brain have to face with this kind of world. So the brain invented some peculiar functions like selective attention and discarding information before processing, or some very heavy conscious process, which is only one exists in one brain, and many subconscious lightweight process, or the dynamics of process as a whole. And the important one is the information generative approach, which because the brain always lack of the information occurs. So, but brain have to process in real time. So the brain always generate information to fulfill the wrapped information. In contrast, the digital computer right now can assume huge resources such as big data and virtual network space. And the problem which should be solved are usually well defined and unimposed. So the world is different. So purpose is different and condition is different. Therefore, the strategies you taken should be different. For example, the homogeneous processing way and not discarding information, but picking up information and using the algorithm. And also the information is not generated, but manipulated here. Therefore, the hardware should be naturally different. This is the hardware for the current computer, and this is hardware for brain. Again, the brain hardware and the functions should be tight connected together. But anyway, our target of the brain-morphic computing hardware is this side, not this side. So, and the function are those functions. Okay, let me give you a little summary of basis of brain information processing. The first one, the mutual dependency of structures and functions. Second one is processing by process as a whole. Okay, this will be done by layered and nested interactions between local dynamics and global dynamics. Third one is an embodiment and restrictions from the embodiment. This gives the emergence of brain-specific computation, as shown before. And there are two worlds. One is internal milieu and one is external environment. The fourth one that I didn't mention so far is sensors and actuators. They should be also brain-morphic. I will show you in the final stage of this lecture after. Okay, so what is the principle and architecture and the hardware for brain-morphic computing? Okay, for principle, of course, we use the word process. So processing through process is important. And complex computations with complex system is the one principle. And that means that we should handle complex dynamics as it is. So reductionism and holism both won't work. And we have to use a robustness inherent to the complex system for the high performance computation. And to do those, we may take the analysis by synthesis approach to extend the design methodology. So those items will give the brain-morphic computational paradigm. And how about the architecture? So again, we should make complex dynamical system. In that kind of very nonlinear, high-dimensional network system, scale matters. So we have to take care of the craftsman. It's the integration of craftsman for the some size. Okay, and we have to take care of the structure and function dependency, such as for example, much scale, much layer, much feedback, and we should use the dynamics for computation. And again, the memory and processing is not separated. Those are distributed and mixed, should be mixed, okay, unlike the Neumann-type computing. And more importantly, the structure and function go together will change through continuous learning, so that the architecture should be time evolving architecture. Unfortunately, there is no design methodology exist yet, so we have to explore those design methodology for the actual design. How about the hardware? So brain-morphic computing hardware should make brain functions to emerge, not the design, but emerge by imitating anatomical physiological structures and mechanisms. And those brain-morphic computing hardware should use process or dynamics for information processing by naturally and directly using the device and the circuit characteristic and dynamics, which actually directly mimics biophysics with device physics. And the hardware should use high dimensional complexity and complex dynamics to take advantage of uncertainty, fluctuation, and noise for the high performance computation. And third, the brain-morphic computing hardware should reflect the latest knowledge from the brain science, especially for high-order brain functions. And finally, the hardware should consider and utilize the effect of the embodiment. Those are some requirements for the hardware. Okay, so let me move on some examples of our research for the brain-morphic computing hardware. Okay, the first example is computation through high-dimensional complex dynamics. Okay, here we think about interaction between conscious and subconscious processes. The conscious process is the high-level, logical, and serial process. So there's just one process in the brain. And subconscious process are low-level, dynamic, and parallel, and there are much more large number of subconscious processes in the brain. So actually, those two processes interact with each other through the bidirectional connections, bidirectional interactions. And we may make an analogy of the conscious process and computation through algorithm, because this is digital process, which is serial, logical, and high-level process. And on the other hand, we can make analogy between subconscious process and computation through dynamics, which is continuous process with the high dimensional process, okay, and highly parallel distributed process. Okay, and the brain actually using this kind of structure, bidirectional interaction of the conscious and the subconscious process to to integrate these conflicting functions together. For example, flexible but consistent, the sensitive but robust at the same time, and dynamic but stable system. And we have adaptation, but system itself is invariant. So I am always I, not changed. Okay, this kind of thing. And to integrate these conflicting functions is very difficult by using current engineering system. For example, if we secure the consistency, maybe flexibility will somehow lost. But the brain actually integrate and making balance between those through this kind of mutual interactions in the conscious and subconscious process. So we take this kind of system to solve bodily assignment problem, which is one of the combinatorial optimization problem. And here we have digital computation, digital computer, and here we have the analog computation through dynamics here. As an algorithm, we used the solution construction and two-op exchange taboo search algorithms. Okay, and for the dynamics, we use the very high dimensional complex chaotic neurodynamics, and we made them interact bidirectionally and solve this bodily assignment problem. Okay, those are the example of the hardware. This is one of them, and this shows measurable result from the hardware. The horizontal axis is the size of the problem. Okay, so vertical axis is the execution time needed. So blue one is the result from the Neumann-type computer, digital computer. As you expected, the time will increase exponentially. However, our system using the interaction between the conscious and subconscious process takes almost the same time, not according to even if the size of problem goes up. So this is one a good example for the power of the brain type computational way. So we changed the way of processing. Okay, so we actually made the hybrid computing system. And here, hybrid means algorithm dynamics, conscious, unconscious, digital analog, Neumann, non-Neumann. So we have Neumann processor, and we have high-dimensional, very complex chaotic dynamic system here. We put them together, and also put here the mutual interactions, and this makes a cooperation between those two different paradigms. Then we got some improvement for the computation. Okay, so let's move on to the second example, which is kind of a low-level example approach for the Brainmorphic computing hardware, which is direct implementation of neuron and synaptic functions and dynamics using spin-orbit torque nano devices. Okay, let's look at some little example of the small network here. We have two excitatory neurons and one inhibitory neuron connected to this neuron. Let's look at this membrane potential here, this neuron. This is a membrane potential. If this neuron receives a spike from the excitatory neuron, the membrane potential goes up, giving the EPSP, excitatory postsynaptic potential. But this doesn't hold, but this decreases accordingly. So this means that this is a leaky temporal integration of the spike. And in contrast, if this inhibitory neuron send the spike to here, the membrane potential will decrease to give the IPSP, inhibitory postsynaptic potential, but this goes back to the resting potential like this. This also shows the leaky temporal integration. And if we have several spikes from different neurons here, then the membrane potential goes up and integrated. So this is a spatial temporal integration of the spikes. And if this the membrane potential crosses some threshold, this gives the high voltage action potential, which is called firing. Then the membrane potential rapidly decreases toward to the resting potential, but usually this goes over down to this potential. This gives the refractory period of the neuron. This overshoot is a refractory period. Give the refractory period of the neuron. So we have at least 5 features of neuron which should be implemented as a hardware for continuous change of membrane potential, spatial temporal leaky integration, and also the spike generation. There's a firing and reset to the quiescent point, and also this kind of overshoot, which is refractoriness. For example, the commonly used leaky integrated fire neuron influence the items 1 to 4. Okay. How about the synapse? Synapse is a part which connect neuron to neuron, and this synapse has 3 features, properties simultaneously. First one is learning. Second is plasticity, and memory. And also those, in addition to the functionality, this includes the dynamics of 3. Okay, so we need such a functional device. One example is the nanoscale device, which is usually non-volatile analog memory. Usually called the memory-resistant devices. Those new devices usually physically implement the second one, plasticity and memory. However, the learning is not inherently realized, but maybe external learning circuitry or the clever tuning of the shape of the impulse, and spikes are needed. So let's look at our device. Our device is spin-orbit torque device, which is actually a nanoscale memory resistive element, which shows analog memory property, and also spatial temporal leaky integration, and also intrinsic. That means we don't need any external circuitry for the learning. Intrinsic spike timing dependent plasticity learning function. This is the test device structure, and you can see the cylinder shape of the device here. If you look at this from the top, you can see that this circle, the diameter of the circle is defined by d dot. If we change this d dot from the larger size to the small size like this, according to this one here, you can have several kind of RI loops, which is a memory loop for the same device, but with different size. You see that the analog memory and some multi-level memory, and finally binary response. So maybe we can use this analog memory property to memorize the synaptic weight value, and we can use this binary response for the neuron fire or non-fire state. Okay, this is a kind of functionality. And how about the dynamics? Okay, this is the property of the neuron in physiological neuron, and the horizontal axis is the frequency of input pulses. So as you see, there is some property for the integrator fire. Leaky integration of the pulses, and the characteristic of the firing probability is kind of like a sigmoidal function. The lower here shows the measured characteristic of our device, which also shows the same shape like this. This goes to saturated around here, so this is almost the same as a sigmoidal function. Okay, so this device also gives the neuron-like dynamics here. And how about a little bit more larger device? So this is the spike timing dependent plasticity, so-called STDP. This is a time difference between two pulses, input pulse and output pulse. And the horizontal axis is how much the weight should be changed. So if the two pulses are causal pulse, so pulse is inputted and outputted shortly after, then the weight change should be large. But in the reverse case, the weight should be decreased a lot, kind of thing. Okay, and our device shows the same, very similar characteristic for the input up two pulses. So this device actually inherently implement or realize this kind of spike timing dependent plasticity. So this is those are examples for the direct realization using the dynamics or physics of the SOT device. And for the synaptic-like device, we do not need any learning circuit and external learning circuits. And so those kind of direct expression of brain process, actually functions and dynamics, will lead to a low power and high scale systems, hopefully. We are working on making the network out of these devices right now. Okay, so let's move on to the third example, which is brain-body integrated whole organism computing. So as I said, I emphasize that embodiment is very important. So I proposed the brain-body integrated whole organism computing framework some time ago. And there we implement not only brain separately, but also integrate the environment and the body as an embodiment for high performance computing. To do so, we need a reference for embodiment. So we have to find out what is happening outside, okay? So here the reference means the state of itself, which is based on the internal milieu. So we are calling this dynamic reference self. So this is the system diagram. We have some reference system here, and those are brain part. And we have body, this is the actuator, this is the sensor. And the sensor input is always coming to the reference self system. And we have, of course, external world. And this computing framework is aimed to improve the performance of those computation through the mutual interactions between external world and internal processing. So this part is very important. So what is the requirement for the components for this dynamic reference self? We have three of them. First one is generation of stable neural patterns. So stable neural pattern. This corresponds to reference self, which is actually in internal milieu. And the second one is a dynamical generation, sensitive and rich variety of neural patterns that represent the external and bodily objects. So this is environment and those are internal milieu. Okay, and more important one, the third one, which actually make interactions between 1 and 2 to generate some states of the network. So, for example, if the input is known or a similar object, the brain should respond consistently. So this is consistency. And if the objects are unknown, or situations abnormal, brain have to respond sensitively and with a rich variety of representations, because we don't know what exists in the outside of the brain, so environment actually. So we need these kind of items. However, these two, consistency and sensitiveness, are actually contradictive properties. So anyway, but we need both of stability, consistency, and sensitivity differentiation at the same time. For that, we propose the chaotic neural network reservoir. Okay, before going into the chaotic neural network reservoir, we just review for the ordinary reservoir neural network framework. Okay, this is the basic construction of the reservoir neural network. We have a reservoir network here, which includes a recurrent neural network, which is connected randomly with a fixed connection weight. And here we have input layer and output layer, and this red arrow are only subject for the learning. And learning is usually very simple learning we can use. So if you look at this structure, this resembles this figure which I showed before as a basic element of the complex network, which is unnested layer of nested layer. So this shape includes the recurrent network without structure, but this is connected through a layered network as shown here. So this is one of the good model for the some basic element of the brain structure. And in the hardware point of view, this Reservoir network is very good suitable for the hardware implementation, because as I said before, the randomly connected recurrent neural network whose connections are fixed. And those connections are actually very sparse. And only output layer here are subject to learning with simple. Okay, so this is very good for hardware implementation. And more importantly, this Reservoir neural network approach actually processing information through transient response, not to the not unlike the attractor network, which uses always attractor. So this framework will give a very quick calculation, maybe real-time processing. Okay. Okay. So there's a co-state property in Reservoir neural network, which is one condition to work the network as a reservoir. So this is actually given by the weight matrix, connection weight matrix in the reservoir layer, using the eigenvalue or singular value. Okay, so in short, this says that the network should be stable and robust as a whole. Okay, this is also called the forgetting property. But remember that we need more. That is a variety of dynamics or sensitivity at the same time. It is kind of easy to introduce complex dynamics in the Reservoir neural network by violating this echo-state property. So we get a variety of dynamics and sensitivity from the Reservoir neural network, but we will lose stability and robustness because we violate echo-state property. So both of them cannot be obtained simultaneously from the Reservoir neural network. Therefore, we proposed a chaotic neural network Reservoir, where each neuron in the Reservoir layer is simply replaced by the chaotic neuron model shown in this equation. And the key parameters of the model is those, and if we tweak those parameters, we can introduce the high-dimensional complex chaotic dynamics into the Reservoir without destabilizing the network itself. So the echo-state property is intact. Okay. So maybe we could get both stability, consistency, and sensitivity and differentiation from the chaotic neural network Reservoir. So let me summarize a little bit. Reservoir computing gives us consistency and robustness, and high-dimensional chaotic neural dynamics gives us differentiation, and sensitivity and high speed, and variety of dynamics, variety of representations. Usually, those two are contradictory. However, through the chaotic neural network Reservoir framework, we can integrate with both of them. That means we can get both of them together at the same time. So, though this chaotic neural network Reservoir can apply to the component to make a components of the item 2 and 3 of the dynamic defined self. So we will use this. to make a dynamic different self. Okay, so how does this Catherine neural network work? This is a simple question, and we did some simple tests. One of them are this one, word recognition. We put 200 neurons in a reservoir network randomly connected, and input layer and output layer we connected, and 0 to 9 discrete words were inputted from here, and we observed that. Then first we use the ordinary neurons in here without any optimization. So the average recognition rate was low because we don't have any optimization for the neural network. But when we just change the neurons in here to the chaotic neurons instead of the ordinary neuron, then we got this kind of improvement. So this result encouraged us, and so we changed the size of the reservoir from 50 to 500, sorry, 5,000. And the bluer results from the chaotic neural network reservoir, and this orange one is a result for the ordinary reservoir. So if you look at this figure, it is clear that chaotic neural network reservoir is better, and more importantly, small reservoir works fine. This is very good for future for the edge hardware implementation. So we made the proof of concept chipset using three-dimensional integrated circuit technology using TSV, and I will not go into this about this chip in this time, but I would say that we made the chip and it works fine, and we tested this with the word recognition. Yeah, actually, the fully integration is currently going. Okay, so let's get back to the brain-body integrated whole organism system computing framework. So as we see, the reference self is one of the important element of this system. So we now just concentrate on this self part. Okay. So this is the example. This gives the example number 4. So which is the brainstem components regarding self. So the self of higher animals are categorized by 3. First one is Prof self, which gives a representation of relatively stable aspect of living organization, such as internal milieu. The second one is a core self, which gives the mutual interaction between living organization and object. Okay, and also temporarily integrate the object and living organization as a representation, and giving a consistent pattern for that representation. And the highest self is called orthographical self, which the human, only human, or some primates only have this kind of self. So our purpose only need this part. So target of our research is in here. One is proto-self, and the second one is a part of the core self, maybe from those 2 items. Okay. So how should we implement this as a hardware? Okay, let's look at the brain. It is known that that kind of lower level selves are realized in the brainstem here, especially for dorsal part of the brainstem. There are several relating nuclei are already spotted, and actually some network structures are relatively well known. Okay, so there you see that the bidirectional connections, unidirectional connections, and lateral connections here. Okay. And let's think about those nucleus. So that here is a very old part of the brain. So the connections in the nucleus are evolutionary already determined, and those nuclei are actually recurrent neural networks. So we may use the framework of Reservoir neural network here, but we have those layered connections here. So we may need multi-layered nested multi-reservoir network to realize this network. And if you look at, if you remember this figure, which is the which gives the basic structure, complicated structure of the brain, this figure resembles this kind of network. So this network in the brainstem is one of the good examples of this kind of structure. So we'll want to make this structure and function together. However, at this stage, this network is kind of complex for me. So I made a more abstract network for this network, consisting of 3 parts. First one is called the reference state representation network, which gives the pro-self. And the second one is a sensation representation network, which is actually represent the external world and the internal milieu. So the input is coming from outside of the brain. And the third one is the important one, which that is current state representation network. So this gives the interaction between A and B. And if necessary, this will regulate this network by using some learning algorithms, learning property. Okay. So if you look at here, we need diversity and discriminability. So for this network, the chaotic neural network reservoir can be used. And also here, we have the interactions between sensitivity, diversity, and consistency and stability, those contradictory properties. So this also can be implemented by chaotic neural network reservoir. For this pro-self, this should be a kind of stable network, so we can make it by the ordinary neural network reservoir or some layered network. Okay. Actually, this research on this is now currently ongoing. So if I got some result, I will show you elsewhere. Okay. Okay. So let me summarize for the hardware itself. Those lines are actually listed for the dynamic inference self. What is dynamic self? I already explained. And one important thing is that the dynamic inference self is essential component for the evolution from an independent system to an autonomous system. Here, independent means is not being dependent on external entity, and autonomous here is self-governing. That means independence of internal elements. So those two are very different, but these days many people use autonomous something, autonomous nothing. But really, in reality, those most of them are actually independent systems. We need actual autonomous system. So to do so, we need some self. So if we make this self for the real-time autonomous edge AI system, which acts on its own judgment, this will have a large variety of application area, such as deep sea or deep space, which are the very remote space, and some simultaneation of operation of many agents like that. But I would stress on that it's important to consider this kind of system in the Brainmorphic computational hardware framework. Okay, so let's move on the third item, which is requirements for the Brainmorphic hardware. Let me mention this very briefly. Okay, so by biological feasibility and computational efficiency should be balanced. Okay, there's many kind of maybe brain type hardware, such as neuromorphic hardware, brainmorphic hardware, brain mimic hardware, but we have to make a balance between biological feasibility and computational efficiency. For example, if we go into too deep in biological feasibility, we may lose the computational efficiency. We want to make the balance between this. To do so, we need to find out a good device which we can use to balance between those two. Okay, so this will be the requirements for device and hardware. Okay, let's go into the last item, which is the architectural difference between brainmorphic and digital hardware system. Okay, this is current the digital centric system. We have a world here, and the sensors and attractors are deployed in the world. And we have the general purpose digital computer here. And for the interface, we have AD and DA converters between them. And usually those sensors actuators does not have memory, processing, and learning. So there is big gap between those two in terms of the representation and also the process. So this gives a big bottleneck. Let's say narrow bottleneck. Okay. Okay, so this is the structure of current brain-inspired AI systems, such as let's say DNA systems. So again, sensors, actuators are deployed here, but something maybe partial memory, small processing, and possibly learning are implemented to those sensors, actuators. And for processing core, those are maybe quasi-general purpose and brain-inspired. And processing the memory and learning are implemented, but usually separate. And interface between those may be not only restricted to the AD and DA converters, but there's still a gap between them in representation and also in process, even though this side is changed. So there's still a narrow bottleneck. For the brainmorphic systems, those sensors and attractors are also that should be brainmorphic. So those sensors, actuators are actually included in the brainmorphic system. And the processing core, which is brain, it should be special purpose. As I said before, there should be a group of craftsmen. And processing the memory and the learning are integrated as a one. And those should be in the system, included in the system. To do so, we may need a self, and we have to consider the embodiment. So if you look at here, there's no boundary or gap between those two in both representation and processing. Our eyes are a very good example for this. The eye started with the photoreceptor cell and combined to the pigment cell. And finally, we got the lens cell. And in the early stage, the eye was in the top of some near the surface of the top of the some fish or something like that. But the eye actually popped out from the brain, and like this. And finally, now we have this kind of eye. If you look at this, the substrate of the eye is the same as the brain, and the processing and the coding of the information is the same in the brain. So there's no interface between this. Here's the eye and the brain. So this is the good example for the Brainmorphic hardware system. So let me give you a summary. Oh, sorry. Yeah. I showed you some basis of brain or Brainmorphic information processing. For one is the structure and function, mutual dependency, and processing by process, and embodiment, and sensors and actuators should be Brainmorphic also. Okay, and how about the hardware? So to make a Brainmorphic hardware, we should take brain scientific approach in addition to the information scientific approach. And we should take an embodiment and using a process for the implementation. We need a novel analog or nanoscale device circuit technology. This will lead the device and circuit-driven innovation. And of course, sensors and actuators should be Brainmorphic. And to make the hardware, maybe to design this hardware, we need a novel design methodology for complex time evolvable dynamic system, which actively use the uncertainty, fluctuation, and variation and noise to improve the performance. Finally, I will show you the different scenarios again for digital computers, Brainmorphic hardware. But here the top-down, and this is the bottom-up approach. But this green arrow, which is the top-down arrow using mathematical model, this is also very important. But this time, this lecture, I didn't mention this arrow. But actually, we should have two arrows here, which will circulate like this from top-down bottom to top-down to realize Brainmorphic hardware. And again, the change in computational principles itself naturally leads to high efficient, high performance computing hardware. So thank you for joining. And this is just a list of our found. So if you have a question, please use the chat box for the question. If you have any question or comments later, I'm happy to receive your message using the email. All right. If not, I will close this session. Okay, thank you very much for joining this webinar, and I would be happy to receive your response using email or something. Okay, so I will return this session to the office, and I will see you again in somewhere. Okay, thank you very much.